Houston Control, Agroviz. No use, it won't even kick-start. Roger, Houston Control. Understand rescue operation commencing. Eat what? This is supposed to be a day trip. Roger, Houston. I'll eat the crew. They don't like it, Houston. Log of disabled space shuttle, Spirit of Agroviz. Mission, commercial experiments. Crew, 1 astronaut. Duty, pilot. Astrohens 1 through 6, mission specialists. Duty, free-fall egg-shape experiments. Payload, 1 crate of popcorn. Assignment, puffed in space advertising campaign. To survive, an astronaut marooned in space needs energy, the ability to perform work. Energy can take many forms, such as light, heat, and chemical energy, which includes food. How long can he survive? It depends on making the best possible use of the energy available to him. What would you eat first? Or does it really matter which option he chooses? It's quite a puzzle. And to solve it, we'll need to take a little side trip to explore how energy flows between living and non-living things. Wood is organized. Its molecules are neatly bound together in a complex order. By comparison, ash, smoke, and gases seem and are disorganized. The molecules are scattered, more random, or disordered. Left alone, all systems tend to move from order to disorder. This movement is inevitable. The only question is, how long will it take? We humans often have an interest in speeding up this process. Why? Simple. Highly organized systems have free energy. Free, meaning available, one way or another, for use. We often encourage energy to flow, or transfer from one form to another. What exactly happens to that available energy? The answer becomes clear when we explore what happens to it in a closed system, like the spacecraft. Since energy can neither be created nor destroyed, it is trapped inside our closed system and simply flows from one form to another. As it flows, it becomes more disorganized or disordered. It's scattered throughout the system as heat. Energy is dispersed in gases, soot, and ash. The measure of this disorder is called entropy. As entropy increases, what happens to the energy? Is it still available? After all, it's still inside the closed system. But, as we all know, it's difficult to boil water after the fire is out. As disorder or entropy increases, the availability of energy decreases. Nevertheless, the energy of a wood fire is not necessarily lost to us forever. For example, soot burns, and so do many gases from a wood fire. So we can reverse entropy by reorganizing matter and putting energy back into the system. But there is a price. The energy is coming from the muscles of the astronaut as he reorders matter. In general, we can reorder matter and energy only by disordering another form of energy. In other words, if we focus on our wood and ash, we can reverse entropy, but only by increasing entropy in another energy form within the astronaut's arm. The trouble is, we always increase a little more entropy than we reverse. There is always a net gain of entropy. No matter how efficiently energy flows in a system, no matter how efficiently we reorganize by reversing the flow, energy flow is never 100% efficient. A little energy always becomes permanently unavailable, lost as heat in the system. So, as energy flows, entropy always increases. And that, at last, is the key to solving the plight of our astronaut. In which order should he eat? For a moment, think of him alone, himself a closed energy system. The life within him means millions upon millions of chemical reactions, each a transfer of energy, each less than 100% efficient. The astronaut quickly loses free energy. To reverse this rapidly increasing entropy, his survival depends on receiving extra energy from outside his closed system. In the same way, entropy threatens the closed system of the spacecraft. Unfortunately, no outside source is available to reverse the entropy. Not for a while, at least. So here's the challenge. Which of these options keeps him alive as long as possible? Start with a unit of corn energy. Transfer it to the chicken. Free energy is lost. Transfer what is left of the energy unit to an egg. More energy is lost. And still more is lost. Energy flow wastes energy at every transfer. So to fight entropy, the key is to reduce the number of energy transfers. The best solution? Eat the corn directly. And the chicken directly. But in what order? Use the same principle. Fight entropy. Chickens are actively alive. They undergo many chemical energy transfers every second, and all of them waste energy. A chicken absolutely races towards entropy, compared to corn, which is dormant life. It can remain organized with available energy for thousands of years. If energy must be rapidly wasted, then it should be wasted inside the astronaut, keeping him alive. To fight entropy, take a chicken to lunch. Take 6. The corn energy will wait. We can think of the spaceship as a simple closed ecosystem, which includes all life forms and their physical environment. Of course, no system, not even a spaceship, can be truly closed. It loses heat to space and receives it from the sun, as does our biosphere, the collection of all the ecosystems which comprise our planet.